Hi, everyone. Welcome to another session of Learning Labs. I'm Kirby Koo. I'm part of the growth marketing team here at Chainguard, and today we have Adrian back again to show us how to build secure and minimal images with Chainguard static images. Before we get started, I just want to draw your attention to your right. There are a couple of icons there. You have the chat box, which is the first one. You have the question box, which is where you can submit any questions. And if you have any questions, we'll make sure to answer them as soon as we can. You'll also see with the question icon, all the questions that have been submitted will be listed there, so we're able to kind of sort and answer them as they come in. And without further ado, I give the stage to Adrian.
Thanks, Kirby. So welcome to the Learning Lab session. Just to give some background, what we're going to be talking about is building secure and minimal images with Chainguard static images. It's a fairly high-level talk. The only real assumptions I'm going to make is that Docker or a little bit of Docker. So if you've done like Docker run and Docker build, that's more than enough. And if you do want to follow along, you'll need a system that runs Docker, an editor, and Git. But that's about it. Okay. So a little bit about me. I'm a technical community advocate or DevRel at Chainguard. I did write a book a long time ago called Using Docker for Riley. If you want to get in touch, you can email me. I'm also on the various socials, LinkedIn, X, Mastodon. My surname is relatively unusual, MOUAT, so it's usually fairly easy to find me. Okay. There we go. So, what we're going to go through today, I'm going to start with a brief introduction to CVEs or vulnerabilities and what they are effectively. And we'll talk about Chainguard images, so what Chainguard images are, how they address the issues we have with CVEs, and then we're going to jump straight into the practical. I'm going to show an example image and how to migrate it to the Chainguard equivalent. We'll be using Go as the example, but hopefully if you use another language like Rust or C that can generate static binaries, this should still be fairly relevant. Yeah, and we'll talk about multi-stage builds and how that gets us to the best result in this case. Regarding questions, I think Kirby's been through that, but you can drop questions into the chat. There's also a separate question option, I think. And I will try and stop and take questions at several points, so please do that. And also, I think there's a couple of people helping that'll be able to answer in the chat as well. But yeah, Kirby, do let me know if I'm going too fast or I've made a mistake or people want me to go back over something. Yeah, so and in the chat, let us know if you're trying to follow along and you get stuck or left behind or something doesn't work. We've got plenty of time for questions and so on. So yeah, more than happy to take those. Okay, so I've been through this already, but for anybody that just joined, if you want to follow along, you will need access to Docker. I think Podman should work as well. I've not actually tested that, but I don't see any reason why it wouldn't. Basic container knowledge. If you can do Docker run and Docker build, you'll be completely fine. You do need Git if you want to follow along and change branches and so on. Okay, so before we go any further, I thought I want to talk a little bit about CVEs and why they're a problem for a lot of organizations and people. So CVE stands for Common Vulnerabilities and Exposures. Essentially, it's known software, bugs, or flaws that have a security impact on applications and systems. And some of them can be really, really significant. So you've probably heard of CVEs like Heartbleed or Log4Shell. And when a CVE gets its own special name, then you know it's something to take seriously. Like the vast majority of CVEs don't get their own name, and they're probably not that interesting or likely to get people hacked, but some of them are is the issue. Anyway, this sort of CVEs and this notification of CVEs gave birth to a whole bunch of security tooling that we sometimes call vulnerability scanners. So things you might have used called Privy, Gripe, Sneak. What this tooling does is it scans container images for known vulnerabilities from various databases like NVD, the National Vulnerability Database, and also GitHub, security advisories, and on that data, it will produce a report of which CVEs it thinks are present in your application or container. So ideally, you're probably thinking, well, I'll do that, and what I'll do is I'll try and make sure there's no CVEs in my image. In reality, that's much harder to do much easier said than done. And the main problem is a lot of base images, like the base images you pull from the Docker Hub today, a lot of them already contain CVEs. So you're starting from a point with these CVEs that you can't get rid of, or you can't get rid of easily. And it's kind of a lot of organizations feel like they're in a place where they don't know what to do, really. They're using these scanning tools, and it's telling them they've got CVEs, and they would like to get rid of them or mitigate them, but they don't even know where to start. Sometimes people start investigating them all, but that's far too much work. And they kind of spin their wheels. It's kind of a difficult situation. So that's where Chainguard comes in, and we try to eliminate these challenges by getting rid of all the CVEs or all known CVEs in the open source software that you consume. So all our images are low to no CVE images, and the minimal and hardened for security. So all our images designed to be secure and provide a secure basis for application deployment. Rebuild our images all the time, like at least daily. And we have images for all your ecosystems and all your programming languages, such as Go, Python, Node, but also third-party open source like Postgres, Nginx, Redis, etc. We do also have FIPS images and commercial software as well. So I pulled up this comparison slide. Looking at these images that were on the slide, I did rerun these numbers earlier on today. But basically, we've got a list of images that you can pull from not just a Docker Hub, but also other registries today. So we can see, if we look at the Fluent Bit image, you can see in the upstream image, there's actually 56 CVEs, including a critical CVE. But in the Chainguard image at the minute, there's 0 CVEs. But not just that, our image, because we have very minimal and small images, is half the size of the Fluent Bit official image. Node is even worse. The Node image is over 1 gigabyte in size, whereas ours is only 136 megabytes, and there's 657 vulnerabilities in it according to Gripe, whereas ours has 0. We also scanned Datadog today. I did do all these scans today, so I actually found that there are vulnerabilities reported on the Chainguard image today. I suspect people are working on those right now, and that'll be triaged by tomorrow or so, I would assume. So it'll be interesting to run a test yourself, if you like, on this image and see how quickly those CVEs are dealt with. And again, the image is half the size of the upstream image. Kafka, very similar story. It's got 1 critical CVE, 7 high, 127 in total. And again, the image is roughly twice the size of ours. I should say we have different tiers of images. So in this talk, we'll be using the developer tier of images, and that's like the free tier. So anybody can use it. You can go and try it today. There's no need. It's not gated in any way. But we also have commercial tiers where you get access to other tags, and also SLAs, and we also have FIPS images and so on. Okay, so like I said, let's jump straight into the practical. I wonder if I can click this link. So what we're going to do is we're going to use this Chainguard GitHub repo. That worked, good. Yeah, so if you go here, if you want to follow along, do check out this repo, Chainguard-dev learning-labs-static. So github.com, Chainguard-dev, learning-labs-static. I guess I can post that in the chat if nobody has already. Yeah, and clone that repo using whichever method you like. I'll probably use this one. Later on, if you want to come back to this and work at your own speed or whatever, do note there's different branches. And these branches are basically the different points that we'll get to as I move through the tutorial. But for the tutorial, we'll just be starting on the main branch. And there's a little bit of description there as well. Okay. So now I've got to try and change to my terminal. Which of course means finding my terminal. Oh, Windows, my bad. There we go. Okay, so you should be able to see my terminal now. Hopefully I copied that. Yes, I did. So I'm going to start from a clean repo. Hopefully everything works okay. Okay, so this is the repo. Very simple Go application in here. We may as well take a look at it. Is this a good size for everybody? I think it looks, oh, we make it a bit bigger actually. Just looking on it, there we go. Okay, so what do we have? CMD server main.go. So this is extremely simple application. Here's the entry point. All it's calling is app run server. If you look at the server, all it's doing is starting up an HTTP server that listens on / and port 8080 and returns the text hello world. So nothing particularly interesting there. It's a regular Go application, so I can even do Go build, what is it, .cmd / server, is that right? And then we get a server binary out. I can run that. Oops, something's already on that port. This is me from earlier, not tidying up after myself. So we can get rid of all of these. So you're seeing behind the scenes now. Okay, so if I start this, that works. So that's me just running it as a binary on my local system. And that's what it does. So this is the initial Docker file that we're going to start from. All it's doing is using the regular Docker Hub Golang image. This isn't our image. It's like the Golang image you might use by default for working with. And very simple Docker file. There's nothing too much wrong with it, to be honest. We set a work there, and we copy the code in, and we build it. And we're going to output this hello binary, and we set the entry point to run that hello binary. Docker build -t learning lab dot. I think that looks about right. Okay, and that was cached on my system, so that was very fast. It might take a second longer on yours. I should also do docker pull Golang and do that again. We could even pass -- no cache just to prove that I'm using like the most up-to-date version of Golang. Okay, so we can run this -d -port. So -p 8080 :8080 is saying take port 8080 in the container and expose it on port 8080 on the host. It's actually, I think the first 8080 is actually the host port, and the second one's the container port. -d is to run it in the background. We're using this Learning Lab image that we just created, and that should be about right. I should have given it a name, really. We didn't, but that won't matter. And that works. So it's a simple Docker file that correctly builds and runs this application. But there are a couple of things that I don't really like about this first Docker file. The first one is it's all based on that Golang image, which means we're pulling in everything in that Golang image. And if we look at it with something like Gripe or Docker Scout, which is another vulnerability scanner. Docker Scout's one of my favorite vulnerability scanners just because I kind of prefer the output. It's a little bit tidier, as we'll see in a second. But if I run Docker Scout CVEs on the Learning Lab image, yeah, it's telling me there's 58 vulnerabilities, including critical vulnerability. And you might be thinking, well, how's that? That's a very simple binary. There's nothing in it. And the answer is, well, it's not coming from my binary. It's coming from like all the other stuff in that Golang image. Also, if I look at it, Docker Images, Learning Lab, it's a pretty large image. This has been cached. I could do no cache to force it to update at 903 megabytes. Just to prove that that we are actually running what I built here. I'll go and pass no cache. It won't take very long. There we go. And that should, create 4 seconds ago. But you'll get exactly the same output on, well, we'll use Gripe this time. If you use Gripe, you do have to pass, and it's not an image in a registry. I think you got to pass the Docker : So I think that's the right syntax. Looks good. Because I create a new image, it's going to take a little second. One thing to note here is it's saying it's found like 248 packages or whatever it was in the end, which is 248 different things in that image, which we don't really need because we're just running the simple Go binary. And if I scroll back up, this is the thing I don't like about Gripe, is that you got to scroll back through all this to find the summary output. I guess I could redirect stuff. There we go. So what's it saying is it found 248 packages and 302 vulnerabilities, including 3 critical, 43 high, 94 medium, etc. So it's a lot of vulnerabilities supposedly in this image, even though it's just running the simple Go binary. Okay, so what's the first thing we can do to try to address this? So all I'm going to do is change from using this Golang image to using Chainguard image, which is just Go, not Golang. So one line change. Let's build it again. We'll call it Learning Lab 2. We'll leave that no cache in place. So this will rebuild everything again. Okay, so that's built. First thing, we should check it runs. We might need to kill the old image first. Docker run. Did I call it Learning Lab 2? Yes, I did. We'll also give it a name. LL. That looks good. Check it works. That looks good as well. Okay, so now the big thing is from just changing that one line in the image, hopefully we'll see a large change in the number of CVEs. Oh, so it's going to be Docker : So one thing there has gone down, number of packages has gone down a lot. So there's a lot less just in that image. So we're only 94 packages. But more importantly, there's no CVEs. So one line change, and we've got rid of, I can't remember how much it was, 600 CVEs. It was a lot. So very simple change, but pretty dramatic impact. However, if I look at this image, images, call it Learning Lab 2, I believe. Yep. It's still 741 megabytes. So it is a couple of 100 megabytes smaller than, or what was that, 160 megabytes, 165 megabytes or so smaller than the previous image, but still pretty large. I mean, if I look at this binary, which is really all we're interested in, it's only 6.5 megabytes, but our image is 741 megabytes. And the reason for that is, in this Docker file, we're using this Go image. We're using the same image to build the code and to run it. So the way we can improve things is by using a multi-stage build. And basically what we're going to do is build this binary and then copy it over into a different image to run it that's much smaller. Right, let's see if I can remember how to do this offhand. From static, and I want copy dash dash from hello to, I'm going to change this to just hello. Right, so I'm going to call this stage builder. And then this is a new stage here where this from line kicks in. And in this new stage, we're going to copy the binary out of here and into this image. So all this image is going to have is whatever's in the static base and this binary, and that's it, nothing else. I do need, I might have to check how to do this. Is it underscore? If this doesn't work, I'll have to go back and check my notes. We do need to do cgo enabled equals 0 to tell Go to create a static binary in this case. I will talk a little bit more exactly what I mean by static binary when I get back to the slides. But for the minute, just trust me that this is enough to create a static binary for this Go application. Some other Go applications, you may find that there's actually a couple more things you need to do to get a completely static binary. But in this case, this will work. Okay, I think that looks okay. You're all going to laugh at me if this doesn't work, which is a definite possibility. Docker build, well, what's the last Docker build? So this is the third one. Let's see if I got it right. That's the line I'm worried about. So that's all built. So that looks good. I suspect the old one's still running. Yeah, Docker. And we will run this. Well, let's actually reuse the last run. So I'm not doing anything different. We're just going to change this image. So check that works. That looks good. So that did work. I did get it right. And it just works exactly the same as before. But the big difference now is if I do Docker Images Learning Lab 3, now my image is only 7.48 megabytes in size. So that's an enormous saving. It's really not that much bigger than the binary itself. There's very little in that image. I'll talk a little bit more about what is in the static image in a second. But yeah, so we've gone from a huge 900 megabyte image to this tiny image, and we should, I should prove it, I suppose. CVEs Learning Lab 3. Yeah, and I guess one thing here is like there's only 11 things, like components within this image. And no vulnerabilities. We can also run gripe. Okay, and that's 0 as well. Right, I'm about to go back to slides, but is there any questions so far? I don't see anything in the chat or kind of sort of Q&A. Okay, I don't see anything. So if anybody has any questions, feel free to drop them now. I'm about to go back to slides, and there will be more of a demo later, though. Living packages in static, that's a good question. We can actually ask gripe what's in it. And I will talk a little bit more about what's exactly is in, I hope SIFT is right. And I'll talk a little bit more about what's in static exactly. There you go. So let's say there's 7. I don't know why it's gone from 11 to 7. Oh, that was Docker Scout, so that's probably works slightly different. Okay, so this is based on gripe. And basically, so we're about to change our static image from an Alpine base to a Wolfie base, but really there's very little difference meaning in that because there's nothing too interesting in this image. I could have used a different variant and you actually see Wolfie here instead of Alpine. But for the purposes of the static image, that makes no difference. But what's in there? Say certificates bundle, standard library, time zone data, and some layout files for the directories. And that's it. Oh, and key, I don't know. Yeah, that's probably for download packages. I don't know who needs that. But that's purely about it. It also does have the Go application. Oh, there you go. The standard lib is the Go standard library, which is figured out from the binary itself. So that's all the packages in that image. Okay, back to slides, if I can figure this out. That looks good. So just to recap, we started with a Golang image, which was 900 odd megabytes in size, and had 302 CVEs according to Gripe. Count was 58, and to be honest, if you look at the Gripe output, you'll see some of them say, what was the output? It says won't fix. And that's really ones that Debian has looked at and decided aren't relevant CVEs. So I suspect this is probably a fairer count at 58. Yeah, and size has gone down from 903 to 741 just by changing to the Go image, and 0 CVEs, and then all the way down to 7.48 megabytes. So it's an absolutely enormous saving in terms of size and CVEs. Okay, to try and explain a little bit more about static. So this is basically about how you compile your applications. We are getting into the weeds a little bit here, so don't worry too much if this doesn't make a lot of sense. Basically, all applications are either dynamic or static, at least in Linux. A dynamic binary means it is dependent on external libraries. So it links against other libraries that you need to have in your system or your application isn't going to run. And that's the normal. Like most binaries will be dependent on things like glibc and other libraries. But you can create static binaries that are fully self-contained. So the binary isn't dependent on any external library. The reason that's not been done a lot historically is because you end up with multiple binaries that all contain the same library. So in most cases, it's a good idea just to have libraries on your system and all various applications can link against them. But in the container world, it makes more sense to have static binaries. Rust and Go, if you build applications with Rust and Go, they are statically linked internally, like as in it's in the sense like if you have a Go library that you're using in your application, that won't be an external library for the binary. It'll be actually compiled into the binary, if that makes sense. It's the same with Rust. But they do link against system libraries, which is primarily libc. And there's two implementations of libc, or the Linux C library, glibc and muzzle. There's probably more, but that's the two major ones. And of the two major ones, glibc is by far the most popular and common. Sometimes you will see people using muzzle. It's basically an alternative C library that's primarily used by the Alpine Linux distribution. And you can use that to create completely static binaries. One thing to note in that Go example that we had, that wasn't using muzzle or glibc, I believe. I think it just, in Go, they've re-implemented various of the various of the kernel calls are made directly from the Go application. But I think in some cases, they'll have different runtime characteristics than perhaps using glibc and so on. So that's why some people won't be using cgo enabled equals 0. I'll get to how we build zero CV images in the end. There's a few things there, so I have a whole slide on it at the end. Some people also try to avoid using muzzle because of compatibility concerns. That can be true. Like, there's nothing wrong with muzzle. I don't want to say anything bad about it. I do note that projects like Node and so on don't officially support muzzle. They officially support glibc as a compile target. Okay, so if you're using the Chainguard static image, that doesn't have a libc inside it. It doesn't have any libraries inside it. Oh, we've not talked about that. So the static image only has enough in it to run the average binary. So some of you might be saying, well, if I have a static binary, I can put it into the Scratch image, and the Scratch image is a completely empty image. And that does work in some cases, but the majority of applications actually need a few more things. What you'll find is a lot of applications require TLS certificates. For example, if you ever going to talk to a secure service, which is the majority of applications. So you really want TLS certificates in your image. But there's also other things, like you probably want the /temp directory, because that's a lot of applications assume that /temp exists, and /home sometimes, and also time zone data and things like that. So that's the kind of thing that's in the static image. So, I mean, it's still very little. It's still only a megabyte in size, but contains enough to run the normal static binary. Now, that being said, there's also like, well, why don't we create an image with just the really common libraries in it? And that's what we've done. So there's also images called CC Dynamic and glibc Dynamic that contain a few more libraries. And one case that's really useful in is Rust, if you don't want to compile against muzzle. So if you are using Rust, you can probably just use the Chainguard glibc Dynamic image. This does depend a little bit on which Rust modules you use, because they could be dependent on other libraries. Otherwise, you can use the muzzle target in Rust, and that will produce a completely static binary. So sometimes if you're looking at Chainguard, you'll hear the term distroless. So our images are very minimal, and this sort of style of minimal images where we only have the bare minimum of the number of dependencies required to run the application is described as distroless. And we take that pretty seriously, right? So if you go and look at the Redis application on a Docker Hub, what you'll find is it doesn't just include Redis, but it also includes various operating system utilities and tools, which in some cases make maintenance easier, and some cases, help make development easier, but they're not needed to run Redis itself. So what we've done is create images that only contain the dependencies that are required to run Redis or Nginx, for example. And we've taken that to pretty extreme levels, as in, like, most of our images default images don't have a shell or package manager. We do create latest-dev variants. So if you do need a shell or a package manager, you can just use the latest-dev variant. And that's totally fine to use even in production. Just be aware that it does have a shell, which has some security implications. Like, for example, if an attacker was to get in there, they'd have a shell they could use in, for example, living off the land attacks. But it's still going to be a lot more secure than the average image from the Docker Hub and so on. Okay, so one reason people don't want to use distroless is because they say it's hard to debug distroless images because there's no shell. And I want to explain what's meant by that and some of the ways around it. So I'm going to go back to my shell. Oh, gone too far. Is there any questions, by the way? Let me check. Oh, I see stuff in the Q&A. Okay, I think we've dealt with that. I'm going to deal with zero CVE images at the end. just let me get my shell. Hopefully I know what I'm doing now. Good. So we still have this running. So this is the completely, this is the image on static, so it's got no shell in this image. So I can do what you would normally want to do, Docker exec, right? That's the way, the default way that people poke at images and try and figure out what's going wrong. So if I try to exec into this container, so it's not, and start a shell, what I get is bin/sh, no such file directory. And well, that's right. There's no shell in that image, so I can't start a shell in the image. Excuse me. So what to do? Right. If you're on Docker and you're using Docker Desktop, you probably have access to the Docker debug tool. I think everybody has access to it now. At one point, it was just you have to be on a subscription. I'm not quite sure of the states at the minute. Yeah, Docker debug, and then of an LL, that will start up Docker debug. And now I do have access to everything. So, that hello binary is a binary inside it, and you can see the various things in the image, which, as I said, is very little. There are also various tools available, and even editors. So that's how to debug on Docker. If you're on, I don't have Kubernetes running at the minute, but if you're on Kubernetes, there is something very simple, similar kubectl debug, and that will start. The way that Docker debug and kubectl debug work is they start in a container, a sort of side container that contains all the utilities that they attach to the main container. So kubectl debug will do something very similar for you on Kubernetes. There's also another tool that I learned about recently called cdebug. Let me see if I can, yeah. So if I do cdebug exec it and ll, I also needed to pass this -- privilege flag for some reason, and that also gets me into the image. Gives me a shell. I'm not sure how many utilities. Oh, there are various utilities there as well. So if you don't have access to Docker debug and you're not on Kubernetes, do try cdebug. And there's links later on in the slides. If there's any questions about debugging, do ask me now. I'm about to jump back to my slides. Oh yeah, first thing I should have said was there are latest -dev variants. So if you're having trouble debugging something, you can just change to the latest -dev variant of one of our images, and that will give you a shell and package manager, and you can just debug with Docker exec or whatever. If not, try Docker debug. If you're on Kubernetes or you don't have Docker debug, either try cdebug or kubectl debug. It's a message. Is there any advantage to including bin/bin/sh? Not enormous ones. It can be a little bit tricky to debug things at times. I think in development, maybe it's handy to have a shell so you can quickly change things and play about with things. One area that can be very important to have a shell is in a Docker file. So like if you're in a Docker file and you want to add more software in your build steps, then you're going to need a shell and a package manager. You may be able to use a multi-stage build, so your final image doesn't have a shell. So at production, I much prefer images without a shell or package manager. But yeah, your ops team may or may not agree. Okay, so to this point about CVEs, how do we keep out CVEs? How do we get to 0 CVEs? There's sort of 3 or 4 things, but the 2 important ones account for sort of 90% of how we get rid of CVEs, and there's things that you can do yourselves in most cases. So the first one is cut down the number of dependencies. By just having less stuff less software in our images, taking this distroless minimal image approach, we cut down the number of CVEs. We cut down the number of software, the amount of software there is to have a CVE, so there's less CVEs. And it also means, like, if you take an image from like several months ago, which will have CVEs because CVEs are accruing all the time, but there'll be less CVEs in an image with less software. So even over time, our images tend to have less CVEs. Of course, if you use the newest version, there should be low to zero number of CVEs. The second thing we do is we're just really aggressive about keeping things up to date. Like, we're rebuilding our images all the time, at least daily sort of thing. And if like a upstream project of Redis or Nginx or a library or whoever releases like a new version of the software, we immediately grab that and build it and release it into our operating system called Wolfie, or I should say Linux distribution called Wolfie. And like if the Go compiler, for example, if this version of the Go compiler comes out, what that means is we'll rebuild all the packages with the new version of the Go compiler so that you get all the new versions of the standard library in the Go compiler, and that deals with all the CVEs there. And those are sort of strategies you can apply to your own projects as well. I work with a bunch of people at Google, and they used to talk about this idea called build horizon. So, for example, if they have a container or a service in production and it's been running for like over a week or over a couple of weeks, they'll automatically take it down, rebuild it, and start it again. The idea being that, okay, maybe the code that's running hasn't changed at all, but the libraries and so on may need to be updated. And yeah, that's just this really aggressive approach to keep things up to date. The other things we can do is we do sometimes apply patches. So we may like bump a version of a dependency to address a CVE, even if the upstream project hasn't done that yet. But honestly, there's not too much of that. The majority of CVEs are addressed by the first 2 points. We can also issue security advisories because we have our own Linux distribution called Wolfie. What we can do is issue security advisories, and these security advisories are picked up by the scanning tools like Trivy, Sneak, Docker, etc. Great. And what we can say is, okay, so for CVE 2024, blah, 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 on this package, actually this CVE isn't relevant because that CVE is about Windows, and this is a Linux package, therefore it's not a relevant CVE. Or we can say, yes, this is a relevant CVE. We can say we're working on it, and then once we have it addressed, we'll update the security advisory to say, hey, this has been fixed in version whatever. And the scanners will pick that up. And so that's how we get to 0 CVEs. Yeah, that's about it. I'm going to move on to questions in a second. What I do just want to say first is hopefully you've seen that it's really simple to change the Chainguard images. We had just that one line change of changing to use the Chainguard Go image did address all the CVEs and reduce things in size quite a lot. Yeah, we have a lot of images available. If you go and check out images.chainguard.dev, there's like 600 images or so for various applications and so on. If there's images that you need that we don't have, do come and talk to us. And yeah, there's -dev variants for in case you need a package manager or shell. Okay, so thank you very much. Is there any more questions? I see something here. Okay, I think we've addressed that one already. Oh, here we go. What are tools that Chainguard uses to identify CVs? So we do run tools like Gripe internally. Internally, I think we're using more now, but we were very focused on Gripe to begin with. So that's the main one we test our images against. And that usually it's usually a fairly effective tool. They use a lot of databases. The way these scanners work is they ingest databases. So the big ones are things like NVD and GitHub security advisories. But there's several other ones as well. And all the Linux distributions, effectively have the security advisories, which they also ingest. But yeah, we'll run Gripe against things. No problem.
Okay. Looks like Any more last questions for Adrian?
Yeah,
Or
yeah, I can answer that. That's cool. The security advisories are available. Let me see if I can actually bring it up because it's quite interesting. I know I've not shared yet. I just want to find the repo first. Yeah. Does that come up? Yeah. So this is wolfie-dev/advisories. And here we've got a list of all the various packages within the Wolfie Linux distribution. And if you click into any of these, you will find advisories. So most of the time you're seeing like here's, that's an unusual one. Oh, here's GitHub Security Advisory. And we're saying we fixed this in this version, for example. Sometimes you can, and here we're saying that we didn't use this version of the vulnerable code. And things like that. These aren't in order, by the way, so be a bit careful of that if you look at this. But that's basically what security advisory looks like. And it's quite interesting to go and look at. Okay. Back to you, Kirby.
Awesome. Well, thank you so much, Adrian. I hope you all learned something new today. And you'll be receiving an email with the recording as well as our next session, which will be on Node in July. So hopefully we'll see you there. Thank you so much for joining us and have a great day.
Okay. Thank you all. Thanks, Tyson. I got to hang up there. I think I'm just going to close the window.